Hi guys, so it's been a long time since I last uploaded a video. I had exams. Anyways, today we are doing May-June 2015 paper 139701 chemistry. Okay, so let's go to question number 1. The diagram shows the Boltzmann energy distribution curve for molecules of a mixture of two gases at a given temperature. So the temperature is constant, right? It's a given temperature. For a reaction to occur, the molecules must collide together with sufficient energy. Obviously, we need that for a reaction. EA is used to represent the activation energy for the reaction between the gases. Okay. Of the two values shown, one is the activation energy for a catalyzed reaction, the other for an uncatalyzed reaction. So what happens when you add a catalyst, right? Well, the peak remains the same when you add a catalyst because the temperature is remaining the same, right? So the peak, the Boltzmann, the peak. I mean to say the peak would just be this part, but I mean the whole Boltzmann distribution curve just remains the same, okay, with a catalyst. But the difference is that your EA, your activation energy value, it just goes to the left along the x-axis, right? So this is y-axis, this is x-axis. So the activation energy value just goes to the left side. So this is for the catalyzed reaction. EA1 is for the catalyzed reaction, and EA2 is for the uncatalyzed reaction. There's the EA2 is without the catalyst, and EA1 is with the catalyst, right? So what happens in a catalyzed reaction is that the number of molecules with energy greater than or equal to activation energy increases. So you see, this is the number of molecules with energy greater than or equal to activation energy, right? So this whole area. But when there was no catalyst, then it was just this area, right? So that's a smaller proportion of the molecules. So more number of molecules have energy greater than or equal to activation energy if the activation energy value has shifted to the left, right? Which means that basically more successful collisions occur when you have a catalyst. More successful collisions. I have I don't I think I've forgotten to spell today apparently, more successful collisions with a catalyst, right? So EA1 is the catalyzed reaction, and there will be more successful collisions because it's the catalyzed reaction. See, there's a greater area to the left, to the right, sorry. Okay. So which statement about EA1 is correct? EA1 corresponds to a catalyzed reaction, that's right, with fewer effective collisions than the uncatalyzed reaction, that's wrong, right? There are more effective collisions with the catalyzed reaction. There's a greater number of molecules to the right. EA1 corresponds to an uncatalyzed reaction. That's wrong. It's the catalyzed reaction. EA1 is the catalyzed reaction. With fewer effective collisions, that's again wrong. So these two are wrong. Now EA1 corresponds to a catalyzed reaction. That part is right. With a greater number of effective collisions than the uncatalyzed reaction. That part is also right. So C seems to be the correct answer. So I'm just going to circle it. Let's look at D though. EA1 corresponds to an uncatalyzed reaction. Again, that's wrong. With a greater number of effective collisions than the catalyzed reaction. That part is right. But again, you know, it's not completely right. So then D is also wrong. But that means that the answer is C because it's a catalyzed reaction. EA1 is for the catalyzed reaction with a greater number of effective collisions. Okay. And the next question is question number 2. Which diagram shows the correct graph of PV against N for an ideal gas at constant temperature? Okay, ideal gas at constant temperature, PV against N. Well, whenever you think of an ideal gas, you think of this equation, right? PV equals nRT. I suppose it's one of the most famous equations in chemistry. It's a pretty cool equation, honestly. So PV over N equals RT. I'm rearranging it like this because if you think about it, PV is on the y-axis, N is on the x-axis, which means your gradient would basically be y over x, right? So I'm just looking at what the gradient of the graph would be. The gradient of the graph is RT. Okay, R is the ideal gas constant, which is, as the name suggests, it is a constant. So it doesn't change. And they already mentioned that it is at constant temperature, which means like the temperature is also constant. So if RT is my gradient, right? So PV over N, because PV is on the y-axis, N is on the x-axis. RT is my gradient. And since RT is my gradient and R is constant, T is constant, that means that my gradient is constant as well. All right. So if my gradient is constant, that means that, yeah, it's constant, which means B is out and A is out. Now, well, actually, that does have a constant gradient, doesn't it? But why is there an intercept? Like, if you think of it, this equation is similar to y equals mx, isn't it? So um there's no, it's not y equals mx plus c. Like if there was a plus c, then it's just plus 0, right? Like there should be no intercept actually in this equation. So yeah, I mean, I hope it's clear to you guys. But yeah, so ideal gas at constant temperature. Well, for an ideal gas, PV is also a constant, right? Because PV, if you think about it, PV equals nRT. So all of this is constant actually, right? The moles are constant, RT is constant, moles are constant, right? Because it's an ideal gas, you can just assume that the moles are constant. It's a closed system, you know, a fixed number of moles for particles. So if N is constant and RT, as I mentioned before, is constant, then PV should also be a constant, right? So if PV is a constant, and the gradient is constant, well, the choice is between C and D, right? But because PV is also a constant, that means that it can't be increasing really, right? As I showed from this part of this equation. Okay, so nRT, all of that is constant, which means PV is also constant, which means it can't be like this, a straight line. It has to be a straight line with zero gradient, basically. Technically, zero gradient is also constant gradient, I guess, but yeah, the answer is C, basically. Okay, PV is a constant, and the gradient is just 0. I hope that makes sense. I mean, really, you can just remember the shape of the graph. It's not that big of a deal. I just gave a random explanation. Well, not a random one, but a detailed explanation. But basically, the answer is C. Hope that makes sense. Okay. Question number 3. A student performed an experiment to measure the enthalpy change of combustion of ethane. Okay. So, what is ethane? It's just this compound. CH2CH3, right? CH, CH, CH3. That's what it is. Okay, what was the question? I don't know. I also focused on what ethane looks like. Anyways, it's just CH3, CH3. Sorry, I don't know why CH2, CH3, CH3. Anyways, a student performed an experiment to measure the enthalpy of combustion of ethane. He used the following values for the standard enthalpy changes of combustion of carbon and hydrogen. Enthalpy change of combustion of carbon equals minus 394 kilojoules per mole. Enthalpy change of combustion of hydrogen equals minus 286 kilojoules per mole. He calculated the enthalpy change of formation of ethane to be minus 140 kilojoules per mole. What was his experimental value for the standard enthalpy change of combustion of ethane? Okay, so let's just make a test cycle, I suppose. Right? Let me get my pen. Well, not my pen. My laptop pen. Whatever it's called. Right? And anyways, so we can make a Hess cycle like this. 2C solid plus 3H2 gas. Because, firstly I'm going to make the enthalpy change of formation of ethane, right? C2H6. Suppose is a liquid, but C2H6 is a liquid. C2H6 state. Yeah, okay. It's standard temperature and pressure. It's a gas. Yeah, you should know that, I suppose, but I don't know. I mean, it does have like only two carbon atoms, so that makes sense. Anyways, that's not what the question is asking. So let's continue. This is 2CO2 plus 3H2O, right? 2CO2 gaseous plus 3H2O liquid, alright? So this is the enthalpy change of formation, which let's see, which is minus 140, as the student mentioned. Okay, minus 140 kilojoules per mole. So we know that. Then we know what the enthalpy change of combustion of carbon is, because they gave us the enthalpy change of combustion of carbon and the enthalpy change of combustion of hydrogen, right? Which is why I do this test cycle, because I know the enthalpy change of formation of C2H6 ethane, and I know the enthalpy change of combustion of carbon and the enthalpy change of combustion of hydrogen. The only unknown is this, like the enthalpy change of combustion of C2H6, which is what I need to find, right? So, anyways, enthalpy change of combustion of carbon is minus 394, right? And because I have 2 moles of carbon, So I should multiply this by 2, okay? And then the enthalpy change of combustion of hydrogen is minus 286. But because I have 3 moles of hydrogen, I should multiply this by 3, okay? And C2H6, well, I need to find the C2, the enthalpy change of combustion of ethane, right? So I will just take this as X. Okay, now I need to look at what two routes I have here for the Hess cycle. So one is this one, right? And if I start from the same starting point, so this is my start, this is my end, right? So I start, this is one of my routes. So this is my first route, route one. Second route is like this, okay? It has the same starting point and ending point. This is route two, okay? Now I will just put like keep both the sides equal to each other, right? So minus 140, that's from route one, equals to, you're following the direction of the arrow, so I'm not going to change the sign, so it's just going to be minus 394 into 2 plus minus 286 into 3. And then over here I'm going against the, like, that was one part, but then here I'm going against the direction of the arrow, right? So if I'm going against the direction of the arrow, I have to put a minus sign, and then I have x, right? So I'll just put x, okay? Then I will just shift x to the other side. Now what does this come out to be? Where is my calculator? Wait a second, I will find my calculator. Okay, so minus 394 into 2 plus minus 2 into 3. Okay, that comes out to be minus 1646, and then I'll shift this to the other side as well, so it becomes plus 140. Now that is what x is equal to. This is just algebra. Alright, plus 140. So that is minus 1506 kilojoules per mole. Is that an option? It does seem to be an option, doesn't it? So it's B. So my answer is going to be B. Okay, next question. I'll use this color. Which pair has species with different shapes? Okay, so let's look at the first option, BeCl2 and CO2. Okay, so if we look at BeCl2, that's BeCl, well, I think beryllium only has 2 electrons, really, in this outer shell, and then Cl. So there are 2 sigma bonds, basically, and no lone pairs. So if there are no lone pairs and just 2 sigma bonds, that means the steric number, which is basically the number of total number of lone pairs plus sigma bonds for the central atom, or you know the atom which gives the bond angle, sort of. So that's 2, right? So if the steric number is 2, it's just going to be linear geometry, right? So if it's linear geometry, it's going to be 180 degrees. So basically BeCl2 has a bond angle of 180 degrees there, right? Or maybe because they're asking about shapes, I just write linear. Okay. Or you can take the bond angles. Anyway, CO2, O, C, O, and then there's a double bond here and a double bond there. So one carbon has 4 atoms in its valence shell, right? So CO2. And so there are no lone pairs on carbon, and there are 2 sigma bonds, right? Because the other two, if it's a double bond, there will be 1 sigma bond and 1 pi bond. If there's a triple bond, there will be 1 sigma bond and 2 pi bonds, right? So that means that one of these, like, is a pi bond, and one of these is also a pi bond. So we can cancel those out because those are not included in the steric number. It's just that there are 2 sigma bonds. So that means if the steric number, which is the number of lone pairs plus the number of uh, sigma bonds, is 2, then that means again it's linear geometry, the bond angle of 180 degrees. So this is also linear. So these two have the same shape. We need different shapes, so we can cancel that out. Okay. Now let's go to the next option, B, which is CH4 and NH4 plus. Okay, so I'll draw out CH4. CH4. Alright, so it has 1, 2, 3, 4 electrons. Carbon has 4 electrons, forms 4 bonds. Since there are 4 sigma bonds and no lone pairs, so that means steric number is 4, which means that it is going to have tetrahedral geometry, right? So CH4 has tetrahedral geometry, and the HCH bond angle, this bond angle is 109.5 degrees, right? So I'm going to write tetrahedral over here. And then if I look at NH4 plus, NH, H, um, another H, because nitrogen has five electrons in its valence shell, right? So one lone pair is going to be donated to H plus technically, but then because it's being donated, it's just the whole molecule is going to have a plus charge now. And you have three other normal bonds. So you have one dative bond basically, and three normal bonds. All of them are sigma bonds basically. So that means that you have four sigma bonds, no lone pairs. So then it's going to be tetrahedral geometry again, and this NH, so H and H bond angle, sorry, is going to be 109.5 degrees. Okay, so again it's tetrahedral geometry. So that's again the same. So B is not the correct answer either because being two species with different shapes, right? So let's look at option C. We have NH3 and BF3. So N, H, H, H. Well, nitrogen is forming three bonds, and these are sigma bonds, right? And it has one lone pair. So if there's three sigma bonds and one lone pair, then you have a steric number of four, which means that it should be tetrahedral geometry, which means 109.5 degree bond angle. But because of the lone pair, your bond angle actually reduces by 2.5 degrees, approximately 2.5 approximate, and so your actual bond angle is around 107 degrees, which means that it's actually pyramidal geometry. Okay, so NH3 has pyramidal geometry because of the lone pair, right? 107 degrees bond angle. Then we're gonna look at BF3. So B, F, F, F. Or why did I write H? It's F. Okay. So BF3 is in, well, boron is in group 3, so that means it has 3 electrons in its valence shell, which means that it basically is forming 3 sigma bonds and it has no lone pairs. If it has a steric number of 3, that means that it has trigonal planar geometry, right? So if it has trigonal planar geometry, it's going to have a bond angle of 120 degrees, right? This FBF bond angle is 120 degrees. Now, if it's trigonal planar and NH3 is pyramidal, then that means that they're different, right? If they're different, then that means that probably C is our answer. So I'm going to put a tick here and going to mark C as the answer, but it doesn't really do harm to check option D as well, I suppose. So let's check option D, okay? We have SCO2 and H2O. Let's look at it. So S, then Cl on either side. Sulfur is in group 6, so it has 6 electrons in its valence shell. So one is bonded here, one is bonded here. Then you have one lone pair and another lone pair. So there's two lone pairs basically. And that means, so if you have two sigma bonds, as you can see, and two lone pairs, that means your total number, your total steric number is 4, right? So if it's 4, you predict the shape to be tetrahedral at 109.5 degrees, but because there are two lone pairs, so your total bond angle reduces by 2.5 times 2, so that it reduces by 5 degrees basically. So 109.5 degrees minus 5 degrees would end up being 104.5 degrees. So it's actually a non-linear shape, or you could call it bent, or if you want, V-shaped. Okay, you can simply just say non-linear, that works, but or bent. But that's the shape basically. I'm just going to write bent. Okay, and yeah, now if you look at H2O, H2O. O, H, right? So oxygen is also in group 6, so it has 6 electrons in its valence shell. 2 are bonded to either of the hydrogens, one here and one here. And then there are two lone pairs. So that means that you have two sigma bonds and two lone pairs, which means total steric number is 4, which means, again, you'd predict it to be tetrahedral initially, 109.5 degree bond angle, but because of the two lone pairs, your it decreases the bond angle decreases by 5 degrees, so it becomes 104.5 degrees, which means that it's actually a bent shape, or you could also call it non-linear or V-shaped, right? So again, I'm going to say it's bent, and that means these two are the same geometry. So that means D is also wrong, and therefore, again, this all because we eliminated A, B, and D, right? So that means definitely C must be the correct answer because NH3 and BF3 have different geometries. Okay, next question. In which reaction does an element have the largest change in oxidation number? So let's look at the options. Cr2O72 minus plus 6Fe2 plus 14H plus gives you 2Cr3 plus 6Fe3 plus 7H2. Okay, so over here you have Fe2 plus, that's obviously plus 2, and here you have plus 3, right? Iron S plus 3. So that's just a change in oxidation number of plus 1, right? Whereas if I look at Cr2O72 minus oxygen, it's more electronegative than Cr, so we're going to give it the priority, right? So basically, oxygen has an oxidation state of -2 usually, right? So -2 times 7, and then since there are two Cr, I'm just going to take the oxidation state of Cr chromium as X. So then it's going to be plus 2X, and the overall charge of this ion is -2, right? So this is going to be equal to -2. This is how you calculate oxidation states in a compound, sort of. So then I'm just going to carry out the algebra. It's going to be x is equals to plus 12 by 2. So that's going to be plus 6. Okay, so over here, chromium is plus 6. And over here, Cr3 plus is obviously plus 3. So plus 6 to plus 3 is what? It's, well, the oxidation state is reducing by -3, right? So we have changes of plus 1 and -3. Now I'm going to use a different color, light blue. So you have OCl minus and you have ClO3 minus and 2Cl minus. Okay. So OCl minus, well, oxygen again, it will have a fixed oxidation state of -2. We have to find the oxidation state of chlorine, so I'm just going to take it as 2x again, and then minus the whole ion of the charge of -1, right? So I'm going to take it as -1. Then x is equals to -1 plus 2, so x is equals to plus 1. So over here, Cl has an oxidation state of plus 1. Now if I, over here, obviously this is -1. And then if I go to ClO3 minus, just going to do it here. So Cl, I'll again take Cl as X, and then O has an oxidation state of -2. So plus, because there are 3 atoms of oxygen, right? So 3 times -2, and then the overall charge of the ion is -1, so equals to -1. X is equals to -1. Then -6, if you shift to the other side, it becomes +6, so x is equals to +5. So over here, Cl has a +5 oxidation state, okay? Now let's see what the difference is. Okay, so +1 to plus, so this is basically a disproportionation reaction, right? Like chlorine is simultaneously becoming oxidized and reduced. So +1 to +5 is simply, +1 to +5 is simply an increase of 4, and +1 to -1 is a decrease of 2, right? 1 minus 2. Yeah, okay. So if I compare these two, a change of 3 and 1 over 4 and -2, so the biggest change till now is B, right? Because you have a change of +4, whereas this only has 3 and 1, right? So +4. So till now my answer is B, but let's check the other options. So 5Fe2 plus. So this is +2, and over here you have +3, which is the same as in the reaction in A, right? So it's not going to be a change due to Fe, basically. That's going to be the difference, I suppose, if you can point, like, so the largest change in oxidation number, right? Now MnO4 minus. In MnO4 minus, I have 4 oxygen atoms, so 2 times -4. I'm going to take Mn as X, oxidation state of Mn as X, and the overall charge of the ion is -1. So X equals -1 plus 8. X is equals to plus 7. Okay, so over here, my Mn is plus 7, and my Mn2 plus is obviously plus 2. So plus 7 to plus 2 is a change of what? 7 minus 2. So, that's going to be a change of 5, right? So 7 minus 5 equals to 2. So that means till now I can cancel out D as well, because 4 versus 5 is a bigger number, right? So till now my biggest change is in C, but again I will check option D as well. Okay, so let us check option D. I will just choose red color. Okay, so PbO2, again oxygen, I will take it as an oxidation state of -2, because usually oxygen does have fixed oxidation state, except in some cases, like for example OF2. Okay, but anyways, there are two oxygen atoms here, 2 times -2, and I'm going to take Pb as x is equals to 0, because overall oxidation state of a compound is just 0, right? So x equals +4. So over here, Pb has an oxidation state of +4. Sn2 plus, which means this is +2, Sn4 plus, which means this is +4, and this is just an increase of 2, right? Now we have a bigger change in C, which is -5, but let's look at Pb. Pb in the reactants is +2. So +4 to +2 is a decrease of 2, right? So -2, which means again, -2 plus 2, 2 is basically a smaller number than 5, right? So we can eliminate option D as well, which means the biggest change in oxidation number has occurred in C, right? This 5. So then, therefore, C is going to be the answer. Okay. Next question. Question number 6. Which statement can be explained by intermolecular hydrogen bonding? So let's see. We need an explanation of using intermolecular hydrogen bonding. Ethanol has a higher boiling point than propane. What's ethanol? That's CH3, CH2OH, right? So if I look at propane, that's this thing, CH3, CH2, CH3, right? So obviously because it's OH, it does have hydrogen bonding. This, on the other hand, CH3, CH2, CH3 is a non-polar molecule, so it just simply has, temporary dipole, induced dipole forces, basically, weak van der Waals forces, right? Or London, you could also call them London dispersion forces. I like that name, it's cool. Anyways, this can definitely be explained using hydrogen bonding, because the reason why CH3CH2 OH has a higher boiling point than propane is because CH3CH2 OH or ethanol has hydrogen bonding, right? So I would definitely say that A seems to be the correct answer to me. But let's look at the other options, obviously. Option B, hydrogen chloride has a higher boiling point than silane, SiH4. Well, let me think about this. Hydrogen chloride technically, well, it's HCl, which is a polar molecule, so I would assume it has permanent dipole forces, right? Permanent dipole forces. HCl, because the five most electronegative elements are FON, ClBr. If you have FON attached to um, hydrogen, then you have hydrogen bonding. Otherwise, if you have either of any of these attached to like C or H or something, usually then it's just permanent dipole. It's just permanent dipole. So then we have SiH4. That's not the right way to draw it, definitely, but I'm just, that's not the point of the question to draw it properly. But anyways, SiH4 is a symmetrical molecule, and it's just SiH I don't think they have a very large difference in electronegativity, so it's non-polar, so it just has London dispersion forces, okay? Or you could say temporary dipole, induced dipole, or van der Waals forces. But again, there's no hydrogen bonding involved here, right? If there's no hydrogen bonding involved, how can we explain it using intermolecular hydrogen bonding, right? So B is definitely not the correct answer. Then C, hydrogen iodide forms an acidic solution when dissolved in water. Well, if I look at hydrogen iodide, it does not have hydrogen bonding, because for hydrogen bonding you need FON, fluorine, oxygen, nitrogen, either of them attached to hydrogen. Well, that's one of the prerequisites. So that condition is not satisfied here. So hydrogen iodide does not have hydrogen bonding. And when it's dissolved in water, it would basically form ion dipole bonds with water, right? If you're just dissolving it, or maybe actually it would react with water to give an acidic solution. So yeah, but it doesn't. There's no like there's no hydrogen bonding involved in that at all, is there? It's just dissolving, forming an acidic solution, but there's no hydrogen bonding involved at all. So we can also eliminate option C. Okay, let's look at option D, anyways. Okay, option D. So propanone has a higher boiling point than propane. So what's propanone? Propanone is this molecule, CH3CO, CH3, right? And propane is just this CH3, CH2, CH3, right? Propanone has a higher boiling point than propane. Propane, again, you should need FON attached to hydrogen atom for hydrogen bonding, but that doesn't really happen in propane. Right? I can draw it like this as well. So over here you have an oxygen atom, but it's bonded to a carbon, right? It's not bonded to any hydrogen, so it does not have hydrogen bonding. It's just permanent dipole forces, right? And over here, this is a non-polar molecule, right? Of course, CNH don't have very large electronegative difference, so it just has temporary dipole intermolecular forces, temporary dipole induced dipole intermolecular forces. There's no connection with hydrogen bonding at all, which means because these three have nothing to do with hydrogen bonding, then obviously A is the answer, which definitely like ethanol has hydrogen bonding, propanone is non-polar, it just has temporary dipole and induced dipole forces. So therefore, A is the one that can be explained by hydrogen bonding. Okay. Question number 7. Carbon monoxide and methanol can react together to form ethanoic acid. Standard enthalpy changes of combustion are given in the table. What is the value for delta HR to the enthalpy change of standard enthalpy change of reaction enthalpy for the reaction between carbon monoxide and methanol? Okay. So let me just make a Hess cycle. So they've given enthalpy changes of combustion, right? So let me just make it CO2 and H2 at the bottom of the Hess cycle. And I will make arrows from the products, sorry, from the reactants to CO2 and H2 and from the products to CO2 and H2. So considering the combustion of both of them, right? So the enthalpy change of combustion of, now there are 2 moles of carbon here, right? So let me just make this 2 CO2 and H2O, again, how many? 3, 4. So there are 4 H atoms, which means it's probably 2 H2O, right? So hopefully that's balanced. But yeah, not really important for MCQs to balance the cycle, I suppose. But anyways, CO. So there's just 1 mole of carbon monoxide combusting, right? So it's minus 283.0. So I'll just keep it as minus 283.0, not multiply with anything because it's just 1 mole. CH3OH, again, it's minus 726.0. So I'll just write this over here. I love Hess cycles. Hess cycles, whatever they're called. So this is again 1 mole, so it's just going to be minus 874.1. Okay, and let us see what is my first route and second route. So this is route 1. Start. This is the end, and again from the same start to the same end, but using a different route. This is route 2. All right. So now I'm going to put both those routes equal to each other. So delta HR, which is route 1. Because we can just write it down here. I have space, right? Yeah, space. So delta HR equals to, so over here I'm going with the direction of the arrow, so I will not change signs. So just minus 283.0 minus 726.0. Okay, and then over here I'm going against the direction of the arrow, right? So I just put a minus sign and then minus 874. Okay, if you're going against the direction of arrow, you have to put a minus sign. It has, like, we'll just calculate this out. Minus 283.0 plus, sorry, minus 726.0 plus 874.1. So that is minus 134.9 kilojoules per mole. Okay, and which option is that? That's option B. Okay, so that is your answer. Next, the following reaction was carried out. The concentration of methanol CH3OH aqueous was measured with time t. Okay, which graph shows the relationship between CH3OH aqueous and T? All right. So let's think about this. I mean, D definitely looks wrong. Like, what is that? CH3OH is a product. I mean, this is just really a random thing to have, you know. And this would probably be the graph if it was an autocatalytic reaction. It's hard to pronounce some words on that, but we can't assume that it's an autocatalytic reaction because they didn't say that it's an autocatalytic reaction. So if they didn't say it, don't really assume it, you know. So we can cancel out B and D. Now, if we look at A and C, the thing is that, um, you know, honestly, the rate of reaction, because the rate of production of CH3OH will decrease with time. So it's basically supposed to be a decreasing gradient graph, okay? But over here, like if you look at C, I mean to say, In C, you have a constant gradient for this portion, right? And then you have a plateau. But that's a problem. And why is it a problem? Because as the reaction continues on, your number of reactants reduces, right? Like your reactants become less and less in concentration. If they're less and less in concentration, that means that there are fewer successful collisions, right? So if there are, because there are less reactants, so if there are fewer successful collisions, that means that your rate of reaction basically decreases with time. If you get what I mean, right? So basically, because of that, C is not right because it shows a constant rate of reaction for this period, whereas actually throughout the reaction your rate decreases with time because your concentration of reactants is decreasing as the reaction progresses, right? And so your products will be formed slower if the rate is less, right? And then eventually, of course, it plateaus when you have no more, reactants left. Okay, so A has to be the correct answer, basically. Number nine, question number nine. This is not really in the syllabus anymore, so if you want, you can just skip this because, again, electrolysis is just an A2 part, all right? Not AS, not in the syllabus anymore for AS. But anyways, the correct answer is C, according to the mark scheme. I mean, I would think it could perhaps also be, A, but then, I checked the examiner's report and apparently, because actually if you think about it, you have a diaphragm, right? So then because of the diaphragm, like one, you have H2 produced and CO2 produced. So, um, they might come into contact, yes, but then H2, like according to the examiner's report, H2 just bubbles out as soon as it's formed. So it's not a probable reaction, basically. H2 and CO2. Like, I guess it's more probable that NaOH and CO2 react together. So that's the answer. Anyways, the point is that this is not in the syllabus anymore. So yeah, you don't really need to worry about it too much. But this is the reaction that would occur between NaOH and CO2 if, you know, um, there was no diaphragm. Again, yeah, if there was no diaphragm, then the reason H2 and CO2 would not react is because H2 bubbles out as soon as it's formed, according to the examiner's report, right? I don't know why I do diaphragm earlier, but anyways, this is the reaction that takes place for C. CO2OH plus 2OH. Did I write that right? I missed out NaCl. Right, that's the reaction. Anyways, just skip that honestly. You don't need to worry about it. Why worry about extra things? So next question number 10. 1 gram of a metallic element reacts completely with 300 cubic centimeters of oxygen at 298 kelvin and 1 atmosphere pressure to form an oxide which contains O2 minus ion. Okay. The volume of 1 mole of gas at this temperature and pressure is 24.0 cubic decimeters. Okay. What could be the identity of the metal? Alright. So we have, what are the options? We have calcium, magnesium, these are group 2 metals, right? And then you have potassium and sodium, which are group 1 metals. So if I just, sort of write down probable reactions, so let me assume that a group 2 one would be X. Okay, let me just keep it as X anyways. Okay, I'm just going to keep it as X. If it's a group 2 reaction, then X plus O2 would give you XO, right? Because X2 plus O2 minus, if it's, I'm assuming it's group 2, so that'd just be XO, right? And to balance it out, it's X half. This is for if it was group 2. If it's group 1, like potassium or sodium, then it would be X plus O2. Well, if I have X plus and O2 minus, that would give me a formula of X2O, right? This gives me X2O, which means, how to balance this? Put a 2 over here and put a 1 by 2 here. Okay, now it's balanced. And now what are they saying? Let's look at the options. So 1 gram of a metallic element, which we don't know the relative atomic mass of because we have to find that, right? Reacts completely with 300 cubic centimeters of oxygen, and 300 cubic centimeters of oxygen are there, and it's 24.0 cubic decimeter volume for 1 mole of the gas, right? So what's the formula for finding the moles? N equals V over 24, right? In, at room temperature and pressure, as they mentioned, at room temperature and pressure. Anyways, so if it's 300 cubic centimeters, so 300 into 10 to the power of minus 3 to convert from cubic centimeters to cubic decimeters, and then divided by 24.6. So how many moles of oxygen do I have? So use your calculator, and you get 0.0125 moles. Okay. So in both cases, I'm going to write 0.0125 moles under oxygen. Okay. Because I don't know yet if it's a group 1 metal or group 2 metal. Anyways, now that we've done this part, let us backtrack and see how many moles of X we would have. Okay, so moles of X, if it was a group 2 metal, you have 1 by 2 is to 1, right? Which basically means 1 by 2 is to 1 is the same as 2 is to 1 molar ratio, right? If you multiply this by 2. Okay, so 2 is to 1 molar ratio means that if I have 0.0125 moles of this, I should have 0.0125 times 2 moles of X, right? So do that on your calculator. You get 0.025 moles of X if it's a group 2 metal. Now, if you assume it's a group 1 metal, then 2 is to half. If you multiply this by 2, then you get 4 is to 1, right? So if I have 0.0125 moles of this, I should have 4 times 0.0125 moles of X, which is 0.05 moles. I'm not really worried about significant figures for MCQs, by the way, so don't come at me for that. Okay, anyways, now I have this. What am I going to do next? I am going to calculate the relative atomic mass. So N is equals to M over AR, right? And then AR, which is the relative atomic mass, equals M over N. So if I do it for the group 2 metal, then it will be 1.00, which they mentioned in the question, divided by 0.025. So what do I get? 1 over 0.025 is 40. Okay, so the AR is actually 40, which is actually, if you take the periodic table, it's close to calcium. Then if you do it for the group 1 metal, so it's probably not magnesium if it's a group 1 metal, then it'll be 1 over 0.05, right? 1 over 0.05 is 20. 20 is not close to either the relative atomic mass of potassium or the relative atomic mass of sodium, right? So basically the closest answer I have is A. So because 40 is really, really close to the AR of calcium, right? So I'm going to take A as my answer. Okay? So hope that makes sense. Next question. Use of the data booklet is relevant to this question. So yeah, just get a data booklet. The gas laws can be summarized in the ideal gas equation below. When an evacuated tube of volume 400 cubic centimeters is filled with gas at 300 kelvins and 101 kilopascals, the mass of the tube increases by 0.65 grams. Okay, so this is just they're asking you to just use the equation PV equals nRT. Okay, now they want you to find the identity of the gas, so you basically have to find the AR, or you could say MR. You could think of it as relative atomic mass or relative, or you could think of it as molar mass, mass of 1 mole. So I just think of it as molar mass. Like, it's just convenient to always write MR instead of writing AR occasionally. I just like to always use MR, obviously. But anyways, that's not important for the question. But N equals M over MR, right? So I'm going to rewrite this as M over MR because N equals M over MR, so I can rewrite this as M over MR instead of N. I can substitute this, right? I have to find the MR. So MR, if I rearrange the equation, I get MRT over PV. And then I'm going to substitute my values. So I have 0.65 grams. Then my ideal gas constant is 8.31. Temperature is 300 kelvins. It's already in kelvins. That's nice. Pressure is 101 kilopascals. So multiplied by 10 to the power 3 to change into pascals. Volume is 400 cubic centimeters. To change from cubic centimeters to cubic meters, you have to multiply by 10 to the power of -6 because 1 centimeter is basically 1 meter is basically 100 centimeters, right? So then 1 centimeter will be 1 over 100, or you could say 10 to the power of -2 meters. Then 1 cm cubed will be 10 to the power of -2 cubed meters cubed. That's 10 to the power of -6. That's why I multiply by 10 to the power of -6. So anyways, just use your calculator and find out what is the value of the molar mass. 0.65 into 8.31 into 300. Answer over 101 into 10 to the power of 3 into 400 into 10 to the power of -6. So you get 40.1101 And let me just check the periodic table. Argon has a molar mass of 39.9, which is, it's close to 40.1101. So I am going to say that my answer is argon, okay? Because that's the closest one. So yeah, argon is the answer. Next question. Which oxide, okay, we have inorganic now. Which oxide will produce the solution with the highest pH when it's mixed with water? Highest pH means that it's probably basic, because pH scale is from 0 to 14, right, at room temperature and pressure. So if it's high pH, then probably it's going to be basic, I suppose. Now, Al2O3 doesn't really react with water, does it? Because Al2O3 is insoluble. It's a giant ionic lattice, very very strong lattice, and because of that, it's just not going to react with water really. CO2, on the other hand, this is a reaction. CO2 plus H2O gives a weak acid, H2CO3. Okay, it's a weak acid. It's an acid, so I would probably say it's not the correct answer. But let's see. I mean, we have NO2O, so I would definitely say it's not the correct answer. Why? Because Na2O, the reaction of Na2O with H2O will be what? Na2O plus H2O gives you 2NaOH, which is basic. It's a basic substance. It has a high pH, right? So, as you know from your studies of inorganic chemistry. So probably, C is the correct answer. If I took at SO2 as well, SO2 plus H2O again gives you a weak acid, which is H2SO3. Okay, again, as an acid. So if you compare, an insoluble substance, two acids and a base, obviously the base is going to be the one with the highest pH, right? So my answer is C. Next question, number 13. Barium is a more reactive metal than aluminium. Which method could be suitable for the extraction of barium? So this is more of a IGCSE question, I would say, or like grade 10. All right. So you just have to, because you have to know the reactivity series. So my ninth grade teacher taught me, please send camels, monkeys, and colorful zebras in large, heavy containers soon. I'm not going to write all of it because I just, I'm focusing on carbon really here. Um, because they mentioned carbon in the question, so I'm not focusing about the hydrogen stuff. All right. So basically, this is potassium. I'm going to write some of the elements: sodium, calcium. Monkeys is magnesium. It rhyme. No, it doesn't rhyme, but it's just catchy. All right. That's why I remember the reactivity series, because it's just such a funny sentence. Okay, please send camels, monkeys, and colorful zebras in large, heavy containers soon. And then you can also add good panda. That's what I do. So anyways, this is carbon, and this is zinc, and this is iron. Alright? So I'm not writing all of them, but still here because carbon is my main point of interest here. So basically, what happens is that the elements above carbon in the reactivity series cannot be reduced by carbon. Okay, so for these ones, you have to use electrolysis. Okay, but the elements below carbon in the reactivity series can be reduced by carbon. Okay, so you can extract them using carbon basically. But because of that, which method could be suitable for the extraction of barium? Now, what are they saying? Barium is a more reactive metal than aluminium. If it's more reactive than aluminium, aluminium is above carbon anyways, right? So if it's more reactive than aluminium, again, barium then must be above carbon, right? So if it's above carbon, it cannot be reduced by carbon. So we need to use electrolysis. So if they're mentioning reducing barium oxide with carbon, I immediately know that's wrong. Then with reducing barium oxide with aluminium, how would I do that? That's just weird. I don't know. I mean, it's not a standard thing you do. I don't really know what that should be. Anyways, electrolyzing molten barium chloride or electrolyzing aqueous barium chloride. Now, if you think about it, again, this is grade 10 chemistry. That if you have, now if I add more, so please send camels, monkeys, and colorful zebras in large, heavy. Okay, so I also add hydrogen here because hydrogen is also a point of interest now according to the question. So large lead. Okay, so heavy hydrogen. So elements that are above hydrogen in the reactivity series, basically when you carry out the electrolysis of the aqueous solution, if the element is above hydrogen in the reactivity series, then what will happen is that hydrogen will be produced at the cathode. If the element is below hydrogen in reactivity series, like for example copper, or gold, then you will get copper or gold at the cathode. But if it's above hydrogen, then you will get hydrogen at the cathode. So that's why if you electrolyze aqueous barium chloride, because barium is above hydrogen in the reactivity series, so you will get H2 at the cathode, which you don't want. You want barium, right? You want to extract barium. So this is not a viable method. So you need to electrolyze molten barium chloride. So it will be BaCl2 liquid, not aqueous, liquid. So basically my answer is B. Okay. So hope that makes sense. Next question. The compound CH3 thrice NaLCl3 has a simple molecular structure. Sure. Now, which statement about CH3 thrice NaL? So I read it wrong. It was NaLCl3. Anyways, is correct. So let me just. I suppose we could start drawing out this compound. I suppose it has a similar structure to Al2Cl6, right? If you've studied that. So basically, um, aluminium, because it has an incomplete octet, would probably, it has three bonds to Cl anyways, Cl, 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 but then this nitrogen would probably take one of the free lone pair of nitrogen, right? So this is probably how it's made. So Al, Cl, 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 then you have this is one bond, one bond, I'm just going to draw it, okay? And then you have nitrogen, which is attached to CH3, CH3, and another CH3, and then it has three bonds here, but because nitrogen has five electrons in its valence shell, so it has one more lone pair. This lone pair is donated to aluminium, which you can see 1, 2, 3, 4, 5, 6. So it needs two more electrons to complete its octet, which it gets from nitrogen, right? So this is how I would think that this compound is drawn. Anyways, which statement about this compound is correct? CH3 thrice NaAlCl3 molecules attract each other by hydrogen bonds. Well, let me think. I again for hydrogen bonding you need fluorine, oxygen, or nitrogen attached to hydrogen. I have nitrogen here, but it's attached to carbon. So to me, it doesn't seem that this compound really has any hydrogen bonds. So I would cross out this option because it doesn't really have anything to do with this compound doesn't really have anything to do with hydrogen bonds. Okay. Next option. The aluminium atom has an incomplete valence shell of electrons. Well, we're talking about this compound, right? CH3 thrice NaLCl3. And because nitrogen donated its lone pair of electrons, aluminium no longer has an incomplete octet. Right now, it has 8 electrons in its valence shell. So this is now an invalid statement. If they were just talking about AlCl3, I would say yes, but they're talking about this compound now, right? CH3 thrice and AlCl3. So they're wrong, basically. And question option number C, the bonds around the Al atom are planar. If you look at the aluminium atom, it has no lone pairs. Then it has four sigma bonds, right? So the steric number is 4. So if the steric number is 4 and there are no lone pairs, the bond angle is 109.5 degrees, which means it's tetrahedral. And since there's no lone pairs, there's no change in this. It's just 109.5 degrees tetrahedral, right? So if it's 109.5 degrees tetrahedral, that means, well, tetrahedral means that it's not in the same plane, right? Like if I just draw this section of it, then it's Al, and then I'm just going to take this as R, okay? So Al, and then R, Cl, and then Cl, and Cl, right? So 109.5 degree bond angle. So they're not all the bonds are in the same plane. So it's not a planar molecule basically, right? It's tetrahedral is obviously planar. So this option is wrong. So probably D is the answer. And if I look at D, what does it say? Molecules contain coordinate and covalent bonding. Definitely that is true because this is a dating bond, also known as a coordinate covalent bond. And well, that's firstly that if and this is also a type of covalent bond, right? A coordinate covalent bond is a type of covalent bond. So definitely this is right. And even otherwise, like all these bonds are covalent bonds, right? So you have one dative bond and all other covalent bonds. So definitely B is right. Now, next question. The labels had become detached from 4 bottles in the laboratory. A student realized that the contents of one of them could easily be identified because on addition of water it would not give fumes of hydrogen chloride. So which did not give the HCl fumes? Okay, so let us look at the options. Al2Cl6. Okay, let me think about this. Al2Cl6. Well, hmm. Al2Cl6 is actually a dimer, right? Al2Cl6 is a dimer. In aqueous solution, it will first break down into its monomer, which is AlCl3. Okay, and then it will further break down into its ions, which are Al3 plus and Cl minus. Okay, and according to this equation, it will be 2Al3 plus and 6Cl minus for every Al2Cl6 molecule, right? And then what will happen then is that basically this Al3 plus will form um, ion dipole attractions with water, or sort of Ligand substitution perhaps, but that doesn't matter. Anyways, the point is that you have this substance in the water, AlH2O6 3 plus, and this hydrated ion, like hydrated aluminum ion, it slowly releases protons, right? It slowly releases H plus to form an acidic solution. So, for example, the first one you get is AlH2O5. So basically, what happens is H2O starts slowly dissociating into H plus and OH minus. Okay, I mean honestly, it's a vigorous reaction, but anyways, um, so this is the first thing you get. All right, and then it continues on. So you get AlH2O5, OH2 plus, further dissociating to give AlH2O4, OH twice, um, plus H plus. Okay, I forgot to add the H plus here by the way. So yeah, plus H plus H plus. Okay, and then it keeps going on like that until eventually you get Al OH6 3 minus plus 6H plus. So again, you have 6H plus over here and you have 6Cl minus there, right? So then what happens then is that 6H plus plus 6Cl minus for each Al2Cl6 molecule, I mean, you get 6HCl. Okay? 6HCl gas. So definitely because you have HCl gas forming, so you do get HCl fumes with Al2Cl6. Okay, hope that makes sense. Now we're going to look at the other options. Basically, A is not the correct answer. Okay, let's look at MgCl2. Oh, erasing takes a long time. Anyways, so A is not the correct answer. Now let's look at MgCl2. MgCl2 is a neutral chloride, okay, and it dissolves in water to give, well, a nearly neutral solution like pH 6.5. But basically, all that happens is that MgCl2 solid in the presence of water, it just becomes MgCl2 aqueous, really, or you could say Mg2 plus aqueous plus 2Cl minus aqueous. So that's all that happens. It's just dissolving, right? There's no HCl gas produced really. So basically, but the question is that which did not give the HCl fuels, right? So I would say yes, MgCl2 is simply dissolving, right? So definitely, it could be the right answer that they add, because MgCl2 does not give HCl fuels. So I would say B is the right answer. Now, if you look at PCl5, PCl5 is an acidic chloride, and it's a white solid. PCl5 is a white solid. If you look at PCl3, that's a liquid. This is a white solid, whereas PCl3 is a colorless liquid. Okay, so yeah, just differentiate between these two. But anyways, they're asking about PCl5, right? So PCl5's reaction with water would be, it will give you H3PO4, phosphoric acid, and HCl. Okay, and there are five HCl, and then 5, 6, 7, 8. So 8 H atoms means I can balance this using 4. Is it a balanced equation? 4 oxygen, 4. Yeah, it's balanced. Okay. So this is one plausible reaction, or so you get HCl gas. So the another plausible reaction could be PCl5 plus H2O, which is quite similar to the reaction you see in organic chemistry often, which is POCl3 plus 2HCl. This is also a viable reaction, I suppose. So you could get this as well, okay? But the point is that you do get HCl gas. So if you do get HCl gas, then obviously C is not right. If you look at option D, SiCl4, right? So let me see. What will be the reaction of SiCl4 and water? SiCl4, by the way, is also an acidic chloride. It is liquid at room temperature, and it's simple covalent. Okay, so SiCl4 plus H2O would give you SiO2 perhaps plus HCl. Okay, now 4 HCl. So let's balance this. 4 H atoms means there should be two oxygen and two oxygen. Yeah, it's balanced. Okay, again you get white fumes of misty white fumes because you have HCl gas produced. So it does give HCl fumes. So D cannot be right answer either. Another plausible reaction, um, plausible reaction you could write. I suppose you could write multiple reactions, multiple plausible reactions perhaps, but this is another one. So you could get H4 SiO4 plus HCl. Is that balanced? That's not balanced, is it? Still not balanced. I don't know, but you can search the internet. There are probably other plausible reactions. Okay. Anyways, this is the one that I commonly use. It's simple, simple. This one. Okay. So yeah, the answer is B. Next question, transition elements. Oh, I love transition elements. I mean, honestly, yeah, it there's a lot about transition elements in A2 and it's really cool, okay? So yeah, transition elements and their compounds are widely used as catalysts. What is the identity and what is the oxidation number of the element present in a catalyst used in the contact process? Contact process, well, iron is used in the Haber process, right? Haber process and common type process are two common processes that you know since IGCSE, honestly, but iron is not the right answer. Obviously, it's vanadium. Now, the catalyst used is actually called vanadium pentoxide, or you could say vanadium 5 oxide. Okay, so that means it has the 5 indicates that it's a plus 5 oxidation state, right? So it cannot be this. So the answer definitely has to be D. Honestly, quite a simple question. It's just recall, really, right? So yeah, the answer is D. Next question. This question refers to isolated gaseous species. Species F minus, Ne and Na plus are isoelectronic. This means that they have the same number of electrons. In which order do their radii increase? Okay, so let me think. Let me think. Uh, how can I differentiate? I mean, they're isoelectronic, right? So this means this has 10 electrons, this has 10 electrons, this has 10 electrons. But this is Na plus, which means it does not have 10 protons. It has, well, actually, wait. Since it has 10 electrons, that means it has one less electron than proton, right? So its proton number is 11, which I guess you could also check from the periodic table. That would have been an easier way. But anyways, this has no charge, so it also has 10 protons. This has 10 electrons, which means that probably has just 9 protons, right? Now, what does that tell me? That tells me that this, since it has a greater number of protons, the nuclear force of attraction is greater in Na plus, right? So if the nuclear force of attraction is greater, that means the nucleus is pulling the valence shell of electrons more. So I would assume that Na plus would have the smallest radius because it has the greatest number of protons. Hopefully that's the right logic. I don't know, but neon again is, if I go in this order, then basically F minus would have the greatest ionic radius because greatest radius, in fact, I mean, because it's Ne, it's not really an ion, right? So I would just say greatest radius out of these three species because it has 9 protons, which is the least number of protons out of 9, 10, and 11. So it has the least nuclear force of attraction. Okay, so F minus should have the largest radius, and Ne is in between them, both of them. So I'm going to say that C is the correct answer. Hopefully that makes sense. And let's go to the next question. Due to their similar ionic radii, the reactions of lithium and magnesium and their corresponding compounds are very similar. Which statement about the reactions of lithium or its compounds can be predicted from this statement? Okay, so their lithium burns very slowly in oxygen. Well, that should definitely be wrong because magnesium, reacts quite well with oxygen. It reacts vigorously with oxygen. So if it's similar to magnesium, then that's definitely a wrong statement, is it not? Next, lithium carbonate decomposes on heating in a blue Bunsen burner flame, forming lithium oxide and carbon dioxide. So, if I look at magnesium carbonate, MgCO3, yeah, that's right. So Mg2 plus CO3 2 minus, so that gives you MgCO3, right? Then if I decompose this, it gives me MgO. plus CO2, right? So magnesium oxide and carbon dioxide. So what are they saying? Lithium oxide and carbon dioxide, which matches with, well, what would be the probable products of MgCO3's decomposition, right? So that means that B could be the right answer. Definitely. Let's look at option C. Lithium nitrate decomposes on heating, forming lithium nitride, LiNO2, and oxygen. Let's look at MgNO3 twice. Mg2 plus NO3 minus it gives you MgNO3 twice, and that, if it decomposes, it gives you MgO plus NO2 plus O2. Let's balance this. So you need 2 NO2 and half O2. Is that balanced? Hopefully it is, but that's not what the question is asking. So yeah, but we have magnesium oxide and nitrogen dioxide. Yeah, it's dioxide, right? Yeah, two oxygens obviously is dioxide and oxygen. Okay. And what are they saying? Saying lithium nitrite. Well, you don't get nitrite from magnesium nitrates decomposition, so if it's matching, it's because you said this. They said that their corresponding compounds are very similar in their reaction. The reactions are similar. So I would say if I deduce the answer using magnesium reactions, this is probably wrong because I'm getting LiNO2 and lithium nitride and oxygen, which is not what happens for um magnesium, right? Magnesium, you get nitrogen dioxide. Where's the nitrogen dioxide, and why is forming nitrite and NO, LiNO2? That's weird, right? So I'm going to cancel out C. Lithium reacts very violently with cold water, liberating hydrogen. Um, Honestly, magnesium does not react vigorously with cold water. It has a slow reaction with cold water. It reacts better with hot water, right? So if I'm going with what I know about magnesium, then this option D is also wrong, and therefore I conclude that option B must be the right answer. So yeah, B is the right answer. Next question, 19. Two separate tests were carried out on an aqueous solution of a salt which contains only two ions. In each test, the resulting mixtures were filtered and the filtrate solution was collected. Okay, good. Aqueous silver nitrate, which is AgNO3. Yeah. And dilute nitric acid solution. And you get a yellow precipitate. So you know this is the classic reaction, right? So you get a white precipitate or a cream precipitate or a yellow precipitate, right? So which halide must it be? Well, white would be Cl minus, cream would be Br minus, and yellow would be I minus. If it's a yellow precipitate, then that means I probably have AgI, right? So I have Ag plus and I minus basically. And then dilute sulfuric acid, which is H2SO4, and then a white precipitate forms. White precipitate, what ion forms a white precipitate with H2SO4? That is Ba2 plus, right? Because you get a white precipitate of BaSO4 basically, right? So that means that actually they're asking about the filtrate, is it right? So AgI. Okay, wait a second. So they're asking about the filtrate. Wait. Oh wait, no. Okay, it makes sense because they like, yeah, now it makes sense because actually over here you get AgI solid, right? And this is BaSO4 solid. So in solution P, well, the options are Ba2 plus Ba2 plus Mg2 plus Mg2 plus Cl minus I minus Cl minus I minus. So basically, I would assume that for this salt you have Ba and I, right? So Ba2 plus and I minus. So you get Ba2I maybe. Anyways, the point being that if your residue, which is the solid, is AgI, that means the one that has not reacted from this compound, Ba2 plus and I minus, it contains Ba2 plus and I minus. The one that has not reacted is Ba2 plus, right? So that will be in the filtrate, which is the solution. So that's why they said filtrate collected, right? And that makes sense, the option. So then that must be uh, Ba2 plus is in the solution, right? Ba2 plus is in the filtrate. So I would say either A or B is the right answer. Then for solution Q, you got BaSO4 solid, right? So Ba2 plus reacted, which means you have I minus left in the solution, which is in the filtrate. So as it's in the solution, I minus is going to be solution Q, right? So then the answer is going to be B. Okay, next question. An organic compound Z is oxidized by hot acidified potassium manganate 7 and reacts with sodium to give hydrogen. what could be compound X? So first we have this one. I'm just going to draw them out. Um, First we have this one. Okay. Or you could, draw it out fully if you want. I just like skeletal formulas. Okay, they're so pretty and convenient. So yeah. Anyways, is oxidized by hot acidified potassium manganate 7. If you look at this, it is, this carbon is a tertiary carbon, right? Like it has three alkyl groups attached to it. If it has three alkyl groups attached to it, it cannot be oxidized, right? Like if it has three R groups, it cannot be oxidized because where will the oxygen be added? Really, you cannot replace any hydrogen sort of, So yeah, it cannot be oxidized basically because it's a tertiary carbon or tertiary alcohol, I should call it, because it's an alcohol. So let me just say it's a tertiary. 3 degree means tertiary. Yeah. So it's a tertiary alcohol, which means that cannot be oxidized. It does react with sodium to give hydrogen definitely because it's OH, right? So it can become ONA, but the fact remains that it cannot be oxidized. Therefore, A is not the correct answer. So let's look at B. CH3, CH2, CH2, CHO. What's that? 1, 2, 3, 4. 1, 2, 3, 4, and then you have CHO. Um, can it be oxidized? Yes, it can be oxidized into COOH, right? So the aldehyde can be oxidized to carboxylic acid. But the problem is that will it react with sodium to give hydrogen? No, because that's a reaction of alcohols and carboxylic acids, even phenols, in fact, but that's again A2. So let's look at option C then. CH3, CH2, CHOH, CH3. 1, 2, 3, 1, 2, 3. And then you have CH3, but then the third one you have OH. This is how you draw it. Um, 1, 2, 3, 4. Yeah, okay. So will it be oxidized by hot acidified potassium manganate 7? Well, it's an alcohol, but it's not a tertiary alcohol, unlike ASO. Can it be oxidized? Yes, it can. It can be oxidized into a ketone like this. Okay. And will it react with sodium to give hydrogen? Yes, because it's OH, so it can become this thing O and A, right? So definitely this one is right. So C seems to be the correct answer. Let's look at D. Just check. Do it up here. CH3, CH2, CO, CH3. That's a ketone. So 1, 2, 3. Then you have a C double bond O, and then you have a CH3. So will that be oxidized? No, ketones cannot be oxidized. Further, reacts with sodium to give hydrogen. No, that's not a reaction of ketones either. So that means D is also not right. So again, that just confirms because A, B, and D are wrong. C must be the right answer. Okay. So yeah, and let us look at the next question now. The diagram shows a molecule that has sigma bonds and pi bonds. How many sigma bonds are present in this molecule? Okay, this is a very annoying question. So what I'll do is I'll just cut this H2 and draw them out fully so it's easier for me to count. Again, I'll cut that and draw it out fully so that's easier for me to count. Just make things convenient for yourself. Okay. Oh no, my pen is stopped working. Oh no, it's working again. Good. I was concerned for a minute. Not a minute, a few seconds in fact, but who cares? Okay, let's count now. So sigma bonds and pi bonds. So I have to count the sigma bonds. So don't, if there are double bonds, just count one bond because one of them is a pi bond, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I got 18 sigma bonds. So then my answer must be C. Again, you could confirm and count again. Okay? And then I have 1, 2, 3 pi bonds. That's nice. At least I can see 3 pi bonds. Yeah, 3 pi bonds. Anyways. The Finkelstein, I don't know how to pronounce it. The Finkelstein reaction occurs when NaI in propanol reacts with a chloroalkane or bromoalkane. The halogen is directly replaced by I, and the reaction only works for primary halogenoalkanes. Okay. Now, which halogenoalkane would produce compound X? So let me think about this. It only works for primary halogenoalkanes. Okay, so I can eliminate any tertiary ones. So you can just draw it out. That makes things so simple. So let me just see what this one is. Okay, they drew a skeletal formula, so I'm gonna follow suit. 1, 2, 3, 4 in the main chain, 4 carbons in the main chain. Then you have a Br at the end. Then wait, I did that. Did I do that right? Yeah, okay. So then one, let me just label it like this: 1, 2, 3, 4. So on the second carbon at yeah, okay. So there, this one has two branches for the CH3. Okay. And then we have on the second one again we have a CH3, and that is, I think that's the molecule. So if I, it's a primary molecule definitely. So 1, 2, 3, 4, 5, 5 carbon atoms in the main chain. 1, 2, 3, 4, 5, and then I, and then 1, 2. So does that match with compound X? It does not. So A seems to be wrong. Okay, I'll use another color. I don't know if I have space to draw all four of them together, but I'll try. Hopefully I didn't make a mistake in making this molecule. If I did, well, that's sad. Anyways, 1, 2, 3. So initially draw 3, and then CH3 twice means 1, 2, and then this is 1, 2. So second one, I have a CH3 and CH2Br, which means I have a Br like this. Okay. Now it has 1, 2, 3, 4 in the main chain. So 1, 2, 3, 4, and then it will have this and this, and then it will have I. So does that match to compound X? It does not match. 1, 2, 3, 4. 1, 2, 3, 4, 5. So we need 5 in the main chain. So B is also wrong. Now let's look at, I'm going to erase this too. Okay, I don't have space. Hardly. Maybe I should use some other software for drawing instead of using Microsoft Edge. I know that open board is good. I've used open board. In fact, 1, 2, 3, 4. 1, 2, 3, 4. And then like that. Like 1, 2, 3, 4. And the fourth carbon, 1, 2, 3, 4. It has CH3 and Cl. Okay. So then in the main chain it has 1, 2, 3, 4, 5. So 1, 2, 3, 4, 1, 2, 5. And then a Cl, sorry, it becomes I, in fact. And then you have one branch here, one branch here. Does that match with compound X? It does not. What if I'm doing this wrong? It concerns me. But anyways, let's trust the process and cross out option C as well and go to option D. Okay, I am just trusting the process. Let's see if option D gives me the correct answer. 1, 2, 3, 4. 1, 2, 3, 4 in the main thing. Then you have two CH3s here, and then 1, 2, 3. Third one has a CH3 again, so 1, 2, 3 CH3, and then CH2Cl. So this has also Cl. Okay, so 1, 2, 3, 4, 5. I'm in the main chain. Cl down here, and then one branch here and one branch here. Does that match with R? I'm gonna do Cl and should be I. Anyways, is this a match? It is a match. Okay, that makes me happy. The happy face. So D must be the correct answer. Okay, so yeah, D is the answer. So that's nice. Now question number 23. Okay, and ester P, the fruity odor has the following structural formula. Which compounds are produced when P is hydrolyzed using hydrochloric acid? So you're using hydrochloric acid. Okay. So let me see. The ester bond is going to break, right? So this bond is, this is a really pretty color actually. I like this color. Anyways, CH3 is, so you are hydrolyzing it using hydrochloric acid. Right? So this part will become an alcohol. This part will become an what do you call it? Carboxylic acid. Right? So CH3CO. You will get CH from this part. You will get CH3CO OH, okay? And then from this part, you will get CH3 twice, CH, I just write it in the same way they wrote it, and just add OH there. Okay, so you get these two products. And what are they asking? So Which compound produces NP is hybridizing hydrochloric acid. So you can cancel this out. Aldehyde, why would you get an aldehyde? And honestly, ethyl chloride, those are not in the A2 syllabus anymore. But anyways, you don't get that. Really, using hydrochloric acid, no. If you use PCF5, then you probably get that. That's not really a hydrolysis. Anyways, the point is A and B are wrong, okay? Because you don't get CH3COCl, you don't get CH3CHO. Then CH3CO2, which that's definitely right, okay? And the other part, you don't get an aldehyde. And this seems to be right. This matches with this. So these, like, option D matches with both of my products, which I wrote over here, right? So that means that option D is probably the correct answer, okay? So yeah, next question. The naturally occurring molecule civetone is found in a gland of the African civet cat and has been used in perfumery. Okay, I'm just curious, how does that civet cat look like? Oh, it's cute. I mean, a bit scary, honestly, but cute in a way. Not scary, but daunting, like a cute type of scary. That does that look like a cat to you? Anyways, go off topic, but anyways. The naturally occurring molecule. So, which reagent will not react with silicone? 2,4-dinitrophenyl hydrogen reagent that will react with a carbonyl group of ketone or aldehyde, and we do have one here. This is a ketone, so definitely 2,4-DNPH would react. Okay, so we need will not react. Felling's reagent will react with aldehydes. So CHO, basically RCHO, right? Now I have a ketone over here, not an aldehyde, so Felling's reagent will not react with sibitones, which means probably B is my answer. Now if I look at hydrogen bromide, hydrogen bromide, would it react with sibitone? It would. Why? Because if you look here, sibitone has this alkene bond, and since it has an alkene bond, it can undergo HBr can undergo an addition reaction with uh, serotonin. Okay, so basically it does react. That's why I'm going to cross it out. Then sodium tetrahydroborate 3 NaBH4. NaBH4 can reduce an a ketone into a, well, would it be a secondary alcohol, right? I suppose it would be secondary because it has two groups attached, right? Yeah, probably. Yeah. So it would be secondary alcohol. So NaBH4 can reduce ketone into secondary alcohol. So if the reaction can happen, then well, I'll cross the answer out. So basically, why did I put crosses? Man, I mean, it will react, right? So these two reactions do occur. I'm going to put ticks. This reaction does not occur, so I put a cross. So Ferenc reaction is the answer because there's no aldehyde group here. Okay. So yeah, hopefully that makes sense. Next question. Compound X C5H12O is oxidized by acidified sodium dichromate 6 to compound Y. Compound Y reacts with butane 2-ol in the presence of a little concentrated sulfuric acid to give a liquid. Okay, so if this is being oxidized, this is probably, the formula for the general formula for an alcohol, CnH2n plus 1 OH, right? And that will make C5H2n, two fives are 10, and then 11, then OH. So C5H12O would probably be an alcohol, I would assume. So an alcohol, if you oxidize it, would probably give you a carboxylic acid, right? So if I get a carboxylic acid, and then so basically my compound Y is a carboxylic acid. If I'm reacting a carboxylic acid with butane 2, which is an alcohol, then it's probably esterification that's taking place, okay? In the presence of an concentrated sulfuric acid, further gives it away that's esterification to give liquid Z. So what would be the formula of liquid Z? Firstly, it has to be an ester. All of these honestly seem to be an ester. Okay, on one side I should have butane 2-ol. On the other side, I should have, so basically butane 2-ol should be on. So if I have COOR1 and then R2, right? So R2 COOR1. So this is an ester bond basically. So this part. So if I have CO2, then to the left I should have this part basically should be for the functional the sorry not functional group, the R group of the carboxylic acid, and this side should have the alcohol, right? So if I have CO2, they've written in the same formula I've written it. So then on this side I should have butane 2-ol of this. So I should have 4 carbon atoms on this side. Okay. So let me look here. 1, 2, 3, 4. So that's 4 carbon atoms. 1, 2, 3, 4. Okay. 1, 2, 3, 4. 1. two, three, four. Okay, so all of them have four carbon atoms on the right side, but let me just check which one gives me butane 2O. Okay, so I will look at option A first. Let me just draw it out. Um, so CH3. Should I do the skeletal formula or the other one? CH2, CH2. It's just too much effort. I don't like trying to display formulas, but let's just do it. Started doing it. So CH3, CH2, CH3. Now, if I hydrolyze this, do I get butane 2O? Let's see. CH3H, CH2, CH3, OH. Okay, so butane chain is one, two, three, four carbon atoms. Four carbon atoms, and then I start counting from here. Then this is one, two. So that does seem to be butane 2 because the alcohol is on the second carbon atom, right? I'm going like this because priority. But butane 2 also. It does give me butane 2 definitely. So, but then, so probably that means that B is not right because B is different from this, right? So let me just highlight it. So this is also here in C. So I would say either the answer is A or C. Now you can draw out the alcohol for B and D as well and check it out yourself if you want. Okay, but I am going to test A and C now. I'm going to focus my attention on A and C because I've already eliminated B and D, okay? Because those two don't give me butane 2O. So let me look at, where did I erase that, man? Okay, let me look at A and C. And now I have to check whether the this side gives me C5H alcohol, I suppose, plausible product. So 1, 2, 3, 4, 5. 1, 2, 3, 4. Now that's the problem, isn't it? If I did I count this right? So this has 1, 2, 3, 4. 4 carbon atoms on the left side, whereas this is C5H12. Also, it should have 5 carbon atoms, right? So it has to be a 5 carbon atoms. It should be a carboxylic acid that has 5 carbon atoms. Okay, so C is wrong. And if I look at A, then that must be the right answer because my options are eliminated. But if I count this, this has 3 carbon atoms, then 4, and a fifth one. Okay, so it has 5 carbon atoms and it has butane 2. So A seems to be the right answer according to me. So yeah, A is the answer. Nice. Next question. Okay. Alkane X has molecular formula C4H10. X reacts with Cl2 in the presence of sunlight to produce only two different monochloroalkanes, C4H9Cl. So this is basically free radical substitution happening here, right? Both of these monochloroalkanes produce the same alkene Y and no other organic products when they are treated with hot ethanolic KOH, which is potassium hydroxide. What is produced when Y is treated with hot concentrated acidified KMNO4? Okay, so hot concentrated acidified KMNO4, if it's an alkene, that would mean that it undergoes oxidative cleavage, which basically means the double bond is completely broken, right? So yeah, the double bond completely breaks. Okay. Anyways, let's look at this. So C4H9. So if I look at alkane X, it's C4H10. So what could be my possible isomers? Okay, so I have one like this, C4H10. Another one could be like this. Okay, and I don't really see any other possible isomers for this alkane. Um, you know, structural isomers, or even geometric or optical isomers, but basically these two isomers. So this one would give me, so let me just make it on the left side, and I'll have more space that way. So this one could give me this product, or it could give me this product, okay? And then if I treat it with hot ethanolic KOH, what alkene would I get? This one would give me this alkene, whereas this one would actually give me two alkenes. This is one of them, which is same as this one, okay? And the other one is if this Cl is lost and the H over here is lost, okay? H on this carbon atom. this carbon atom is lost. Okay, so then I would get um this alkene. And what did they say in the question? They said no other organic products are formed. They just produce the same alkene Y. And since I get this as well, so I'm gonna say that this is probably not the isomer of C4H10 that we are using. So probably the answer, so probably we are using this one, okay? So now I will draw out the products using this. So firstly I get this, okay, when I react it with the CO2 in the UV light. And the other one I could get is if it attaches here, okay? And then if I do the elimination reaction with polyethanol, if ethanolic KOH, one of the products I will get is this, and from this I will also get the same thing. Alright, these are the same product. Okay, so since I get the same product and no other additional products, you could I like drawing skeletal formulas, but if you want, you could draw the displayed formulas. It's not a big deal. Yeah. But anyways, what is produced in Y is treated with hot concentrated acidified KMNO4. Since I get the same alkene Y, so what is produced in Y is treated with hot concentrated KMNO4. So basically, this is Y, right? So Y is basically this thing. It's this thing. Okay, I'm drawing this over here. So if I treat it with hot concentrated acidified KMNO4, then this bond breaks, right? It breaks. So what do I get? Firstly, because this is a secondary carbon, it has two R groups attached to it on either side, so it's going to become a ketone. So it's going to become a ketone. On the other side, you have no R groups attached. It's just CH2. So I'm going to get CO2 from that. I get CO2 and this ketone, which is propanone. So CO2, so I can cross out C and D, and I get propanone, which is B. So B is my correct answer. Okay, next question. The compound aspartame is widely used as a sweetener in diet soft drinks. Aspartame is chiral. There are no chiral carbon atoms in C6H5. Okay, and how many chiral carbon atoms are present in a molecule of aspartame? Okay, so we're ignoring this 6H5. And how many chiral carbon atoms are present? Well, there's one here. It's one, and we're just counting the carbon. Yeah, so one here, and that seems to be it. Let me just look more carefully. Yeah, okay, I found another one actually. This one. One and two. Is there any other one? No, I can't see one here or here. That's double bond. Chiral carbon atom means that it has to have four groups bonded, four different groups bonded, in fact, and it has to be, all sigma bonds, all single bonds, obviously, because there are four different groups. So there are no double bonds. This can't be it. This can't be it. And so I just see two. So I'm gonna say the answer is B. Okay. Next, tertiary bromoalkane, indicated here by C. The R reacts with aqueous NaOH. The mechanism has the reaction pathway below. Which point of the diagram is correctly identified? Okay, so these are all intermediates that they've mentioned. Now, if I think about it, what did they say? They said it's a tertiary bromoalkane, right? If it's a tertiary bromoalkane, that means that it will undergo SN1 mechanism. SN1 mechanism, because what does a tertiary bromoalkane mean? It means that it has um, three R groups, right? And so that means that it has a highly stable um, carbocation intermediate, right? So if it has a highly stable carbocation, it will form a very, very stable intermediate, right? So whereas a primary bromoalkane would undergo SN2 mechanism, which means it's just a transition state, not an intermediate. So since it's a tertiary bromoalkane, it will undergo SN1 mechanism, which is two-step mechanism, and so I can cross out B and D because they show transition states, not intermediates. Okay, so A and C are probably my right answer, but let me see which one is the right answer actually. So X is a peak. I would probably assume it's for like the activation energy, right? So there are two activation energies, right? One here and one smaller one here from the intermediate to that, and basically this is just for the activation energy. So X cannot be an intermediate. Y, this little plane here, I would forgot that or plane, a turning point, whatever it's called, man. But this represents my point where my intermediate is present. So this is my reactants, and this is the intermediate and this products. Okay, so Y is C plus. X is wrong. Y is my tertiary carbocation intermediate. Okay, so C is the correct answer. Next question. At least that's what I think. Um, 4 drops of 1 chlorobutane, 1 bromobutane, and 1 iodobutane were put separately into 3 test tubes containing 1 cubic centimeter of aqueous silver nitrate at 60 degrees Celsius. In each case, a hydrolysis reaction occurred. R represents the butane chain C4H9 and X the hydrogen atom. Okay. The rate of formation of cloudiness in the test tubes was in the order RCl is less than RBr is less than RI. So basically, RI, like it was the easiest to hydrolyzed or the greatest rate basically, right? Greatest rate of formation or like the fastest, like it was hydrolyzed the fastest. Uh, yeah. Anyways, and this was hardest to hydrolyze. Okay, so if you think about it, what are the options? The bond energy of Rx decreases from RCl to Ri, the first ionization energy and solubility and bond polarity. Okay, so ionization energy has nothing to do with it. I mean, really, there's no involvement of ionization energy here, is there? It is, we have Rx here and then AgX there. Where do you get ionization energy of X, the halogen? Right, so that's wrong. The solubility of AgX decreases from AgCl to AgI. That's also wrong. There's no here, what to talk about solubility really. I mean, talking about AgX, I would want to talk about the classic thing you think about is again they're talking about bond energy and bond polarity. Both are valid answers. Let me just read them carefully. Are they valid answers? Bond energy of Rx decreases from RCl to Ri. So if I think about it, fluorine, then chlorine, then bromine, then iodine, right? Then acetylene. So down the group, your atom becomes bigger, right? So if the atom becomes bigger, the the bond length is greater, and so the bond and like the bond strength is less, like the bond is weaker. So the bond energy of Rx decreases from RCl to Ri. Sure, it does. The Rx bond polarity decreases from RCl to Ri. Okay, okay, they talk about bond polarity. It's not really much to do with bond polarity. I mean, bond polarity is not a big deal here. I mean, really, they're all quite polar. The main thing is about bond energy. So B, C, and D are all crossed out. The real answer is A, right? I would say because it's talking about even if they talked about bond length, I suppose it wouldn't be a correct answer. But they talk about bond energy, which is the same, really same concept in essence. That since the bond length is increasing down the group because the size of the halogen atom is increasing, then the bond energy will decrease because the bond strength is decreasing, right? So the answer is going to be A. All right. Next question. Malic acid occurs in apples. Under suitable conditions, which substance will react with only one of the OH groups in the malic acid molecule? So the malic acid molecule have one OH group here, another here because COOH. That's technically an OH group, I suppose. Yeah. So COOH, and then you have another OH group here, right? So it only reacts with one of them. So this one, Cl2O72 minus an H plus. Isn't that just the answer? Because honestly, CO2H cannot be oxidized further, so these two are wrong. But then OH, this can be oxidized further because this is a primary alcohol, right? This alcohol, like the carbon that is bonded to it, has two other carbons attached to it. So this could be oxidized to a ketone, I suppose, right? So you will get a ketone from this, whereas these two would not be oxidized. So probably A is the answer. Let's look at Na. Na would react with all three of them. It reacts with alcohols as well as carboxylic acids, right? So B is definitely not the correct answer. NaOH would react with both the carboxylic acid groups, right? So that is also not the correct answer because they said only one. We didn't specify only one type, they said only one. So PCl5. PCl5 would react with again both of the carboxylic acid groups. That's actually an A2 reaction, which is carboxylic acid when they react with PCl5 they form something called an acyl chloride. So RCO OH plus PCl5 actually gives you RCOCl plus POCl3 plus HCl. That's A2 reaction, so don't worry about it too much. But yeah, basically those both of them are going to react and the alcohol will not. Oh, actually, wait, the alcohol will also react. That's an AS reaction. Yeah, yeah, the alcohol will also react, right? With PCl5 plus ROH again, that alcohol gets replaced, so it becomes RCl plus POCO3. I'm not really checking if my equations are balanced, by the way, so yeah, but hopefully balanced. Anyways, so PCl5 will react with all three of them. We can just clarify because I think I said it wrong before, but yeah, it will react with OH as well as CO2H, right? So that's wrong, and so the answer is going to be A because obviously carboxylic acid cannot be oxidized, but OH can be. The secondary alcohol can be oxidized, right? So yeah, A is the answer. Next. Where in this section again, this section is not anymore. I mean, you do still have 40 MCQs, but the thing is that you don't have 1, 2, 3, 1, 2, 3, right? You just have A, B, C, D questions. But again, I like to practice this section because you could technically get questions like A, B, C, D, and then A is like statements 1, 2, 3 are correct, and 1, 2 are correct. Like they could say three statements, right? So technically, you could get these type of questions still, just in an ABCD format, if that makes sense. Anyways, the technetium, the technetium, how it's pronounced, 99 isotope 99 Tc is radioactive and has been found in lobsters and seaweed near to nuclear fuel reprocessing plants. Which statements about an atom of 99 Tc are correct? Okay. Let me just get your periodic table, guys. Okay. So, is it there in the periodic table? Of course, it probably is. Would it not be? And I see. Did they state anything about there is? I hate finding random elements in periodic, but although periodic is very convenient, so take that. Okay, I found it. It's under manganese. Manganese. Just if you guys also had a hard time finding it, but yeah, it's under manganese. Okay, technetium. So technetium has 43 protons according to my periodic table. Okay, so I'm going to write it as I'm going to write a 4. Will it fit? Make the screen bigger so I can fit 43 here. Okay, so 43. Now, we statement about an atom of 99 Tc statements about an atom of 99 Tc. Correct. It has 13 fewer protons than neutrons. Okay, so 43 protons, and obviously because it's a neutral atom, 43 electrons. Okay, and then how many neutrons would there be? That neutrons would be 99 minus 43. So what's that? 99 minus 43 is 56. You know, I could have just done mental math. I don't know why. You become too reliant on calculator. That's sad. But anyways, let's continue. Now what's the difference between 56 and 43? That is 13. So 56 and 43 is a difference of 13. So it has 13 fewer protons and neutrons. So 43 plus 13 will be 56, right? So 13 fewer protons and neutrons, that's true, right? Then it forms 99 Tc2 plus, which is 45 electrons. Tc2 plus means it loses 2 electrons. If it loses 2 electrons, then that means it will get 41 electrons, right? So 99 Tc2 plus has 41 electrons, which means this is wrong. It has 56 nucleons. No, it has 56 neutrons, but in total it has 99 nucleons, right? So this is wrong as well. So only A is correct, only one is correct, which means D is the correct answer. Okay, next question. Nitrogen exists in air as covalently bonded diatomic molecules N2. Very nice. That's definitely true. Uh, Even though I can attest the trueness of this statement, although I can't see nitrogen. Which features are present in one N2 molecule? N2. Okay. So this is how you draw an N2 molecule, and then it has. I mean, well, let me take a look. Should be fine, honestly. Let's draw it like this. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2. Yeah, the octets are complete. So I would say this is a possible representation of N2. So it has 3 pi bonds. Yeah, I drew 3 pi bonds. Wait, it's a 3 pi bonds. That's wrong. See, that's just why you should be very, very careful. Because see, one of these is, so if you have a triple bond, then you have 1 sigma bond and 2 pi bonds. If you have a double bond, then you have 1 sigma and 1 pi. If you have, what happened? That's sad. If you have a, let me erase that. And if you have a single bond, then you just have 1 sigma bond. Sigma bond. Okay. I am having computer issues. But anyways, it's okay. So I have 2 pi bonds, which means that statement 1 is wrong. Then you have 3 shared pairs of electrons. 1, Yeah, this is one pair, two, second pair, third pair. Yeah, that's right. Two lone pairs of electrons. Two lone pair. Yeah. Okay. So if two and three are right, that is C. Okay. Next, question number 33. I'm going to use this color. When dilute acid is added to an aqueous solution containing nitrite, ions, and O2 minus, a mixture of gases is produced. Which statement, which statements correctly describe the process? Okay. Some nitrogen atoms are oxidized and some nitrogen atoms are reduced. I don't know. Let me see. So oxygen, it has a -2 state, oxidation state, so -2. And because there are two oxygen atoms here, I'm going to make multiply by 2. And then nitrogen is only one atom, so I'm going to make it X, like take X as the oxidation state of nitrogen. And then the whole charge of the ion is -1, so I'm going to take this as -1. So X is equals to -1 plus 4 equals to +3. So over here, it's +3. H plus over here is +1 and over here is +1, so nothing, there's no change. Oxygen is over here -2 and -2, so no change. If there is any change, even here it's -2 and -2 oxygen. So if there is any change, it's going to be in nitrogen. So maybe this statement is right. If basically this means that a disproportionation reaction is occurring. So the same substances simultaneously oxidize and reduce. Same species simultaneously oxidize and reduce. That species is nitrogen. And over here, because oxygen is -2, and the overall charge of the compound is 0, so -2 plus x equals 0, x is equals to +2. So this is going to be +2. And over here, again, I'm going to do the same thing. So two atoms of oxygen and, the oxidation state of oxygen. It's funny though, right? Because oxygen, like even oxygen does not have a fixed oxidation state. That's funny. But anyways, 2 into -2 plus x is equals to 0, x is equals to +4. So this is going to be +4. Okay. So over here, there is oxidation taking place because the oxidation state is increasing number. I mean the oxidation number. And over here again, it's ox. Wait, what? Did I do this right? Let me see. Oh yeah, okay. I'm just bad at locating arrows. So this was the arrow I was supposed to make from the reactants to the products, man. But here, because the oxidation number is decreasing, so it's reduction. So oxidation is taking place and reduction is taking place both of nitrogen. That means this is right. It's a disproportionate reaction. The H plus aqueous ion is oxidized by NO2 minus aqueous. Now, as I told you before, this H also over here has +1 oxygen state, and over here as well it's +1 oxidation state. So H plus is not oxidized at all or reduced, so this is wrong. If 2 is wrong, 3 must be wrong as well because my options. So the H plus aqueous ion acts as a catalyst. That is wrong because if it was a catalyst, well, I mean, assuming that this is a main reaction, so either H plus should be on both sides or it should just simply not be included because a catalyst is unchained by reaction, right? It looks like it's a reactant here, which is not. Okay. I mean, it's right, it's just not a catalyst. Alright, so the answer must be D. It's been such a long time since I've made a video that I don't even remember which ones are A, B, C, and D. Like what combinations. Right? Anyways, which physical properties are due to hydrogen bonding between water molecules? Water has a higher boiling point than H2S. Okay, so that is definitely true because, as I mentioned earlier as well, that when do you have hydrogen bonding is when you have the three most electronegative elements, one of the three most electronegative elements, F, O, or N, attached to bonded to hydrogen covalently, right? So then you can have hydrogen bonding in the molecule. And over here you do have that. So you have oxygen bonding to hydrogen, so you do have hydrogen bonding in water between water molecules. Okay, it's an intermolecular portion. So between water molecules, H2S on the other hand it's sulfur, right? So well, I think it's a non-polar molecule. Honestly, if I'm not wrong. Uh, yeah, H2S is a non-polar molecule. So, because there's not much electronegative difference, I think, between S and H, right? So, definitely, um, boiling point depends on the strength of the intramolecular forces, right? So, if water has hydrogen bonding that's stronger than London dispersion forces, so obviously this is due to the hydrogen bonding with water molecules, right? And then ice flows on water. Yes, that's true. Ice does float on water. And why is that? Rho equals m by v, right? So mass of water and ice is the same, but the density of ice is less than water. And since the density of ice is less than water, that means the volume of ice is less than water is more than water. So the volume of ice is more than water. Actually, that's why the density of ice is less than water. And why is the volume of ice more than water? Is because basically water is a liquid, right? So the hydrogen bonds are a bit more like they break and they reform and they break and reform, right? But then in ice, because ice is a solid, so the bonds are more permanent, kind of, okay, because yeah, the molecules are less free to move, so the bonds are more permanent. So ice just occupies a greater volume, and it also has something to do with hexagons, as I remember, but I don't really remember that. You could again check that on the internet. But yeah, it's really cool. Something related to snowflakes. See, there was this book I read, which was Physics of the Future by Michio Kaku. So if you want to read that, you can. It had something about more detail about this, but yeah, so basically, yeah, ice is less dense, and that's due to hydrogen bonding. Again, as I explained, because there's stronger, not stronger, but more permanent hydrogen bonding in ice. Okay, so the volume is greater for the density of ice. Yes, that's related to hydrogen bonding. And then the HOH bond angle in water is approximately 104 degrees. Yes, that we already mentioned that in one previous question, I think, as well in this paper. But this is a sigma bond. This is a sigma bond, two lone pairs of oxygen. So that means two sigma bonds plus two lone pairs means it has a steric number of 4. And because of that, you would assume it would have a 109.5-degree bond angle. But because of the two lone pairs, the bond angle reduces by 2.5 times 2, which is 5 degrees. So then it becomes 104.5 degrees, which is approximately 104. I mean, if you round it down, which is what we've done. I mean, they said approximately, so it's fine. So basically, all three statements are right, which means the answer is A, I think, right? Yes. Okay. Next question. Under atmospheric conditions, okay, under atmospheric conditions, so I would assume that these reactions can occur in the atmosphere. Or maybe they mean atmospheric pressure, I don't know. But anyways, let's just read the question. In which transformations is sulfur dioxide involved as either a reagent or a catalyst? Okay, so NO2 to NO and NO2 NO2. Okay, that's not related actually, so I'll just write them together. NO2 plus SO2, right? NO2 plus SO2 gives you NO3. Is that right? No, it's not right. Because this is actually the oxidation of sulfur dioxide to sulfur dioxide, right? So it's NO plus SO3. Yeah. And then in the next step, you get NO reacting with half O2 to give you back NO2. So basically, NO2 and NO are acting as catalysts because these two can be cancelled out, right? Like left and right, they're the same. So you can just cancel these out. So it's acting as a catalyst. But is sulfur dioxide involved? Sulfur dioxide is involved in this step, definitely. So this is right. And is sulfur dioxide involved in this step? Well, I don't see any sulfur dioxide. It's also wrong, okay? And last one, CO to CO2. That has nothing to do with sulfur dioxide. Oh, CO2 is half of gives you CO2, okay? It has nothing to do with sulfur dioxide at all. And so the answer is just D because only option 1 is correct. Okay, next question. The element astatine is below iodine. That's a nice thing. They wrote a question about astatine because we talk so much about fluorine, chlorine, bromine, iodine. People always forget about poor astatine. So good that they made a question about astatine. Anyways, the element astatine is below iodine in group 7 of the periodic table. Which statements concerning AT can be predicted to be correct? AT2 reacts with hydrogen more slowly than I2 does. Yes, because reactivity decreases down group 7, right? That's an IGCC concept. So definitely that would be right. So the first one is right. And then AT minus ions react with I2 aqueous to form AT2 molecules. Let me think about that. So AT minus ions react with I2 to form AT2 molecules. This is probably to do with the strength as oxidizing agents, reducing agents, and stuff, right? So basically, down the group, like if I'm considering F2CO2, Br2, I2, A2, these are all like the pure elemental states, right? This has zero oxidation state, and then they can become F minus and all, right? So if you add to A minus, so then this will become minus one oxidation state. So this is basically 0 to minus 1 will be reduction. So if they are being reduced, like F2 plus 2 E minus gives you 2F minus, that's reduction. So that means they're oxidizing agents. This is the strength, the reactivity decreases on the group. That means they become weaker oxidizing agents down the group, right? So if they become weaker oxidizing agents down the group, Then on the other side, if you have the ions, which are F minus, Cl minus, Br minus, I minus, what's the last one? At minus, if that's the question. And then those become stronger reducing agents. Okay, stronger reducing agents, I would assume. So then At minus ions react. Why did I erase that? I was going to use that information. Acha. Which statements concerning At can be predicted to be correct? 82 react, reject that. At minus ions react with I2 to form 82 molecules. So At minus reacts with I2. So I2 is a weaker oxidizing agent, and then At minus can react with it to form 82. At minus is a stronger reducing agent than I2 right now. So then if At minus, it's definitely a stronger reducing agent, so it can definitely make I2 into I minus. So that is what will happen. I believe this reaction is plausible because At minus, like I wrote down the trend, right? So stronger reducing agents. If At minus is a stronger reducing agent than I minus, then At minus plus I2 should give you the reaction should be plausible, okay? And then 2I minus plus 82. So yeah, by that logic, I think this reaction is plausible. On the other hand, you could use another logic, which is that they become weaker oxidizing agents. So I2 is a stronger oxidizing agent than 82. So if you react I2 with a salt of 80 minus or just 80 minus, aqueous or whatever, then I2 should be able to displace 80 minus for salt, and you get 2I minus and 82. That's again, that's the IGCSE concept. But again, you could use the reverse logic, which I used here, or you could use the IGCSE logic. Okay, so here, so I2 can displace 80 minus. Okay, so basically 2 should be right. Next 3, A 82. That's 82 not A2. 82. 82 is a dark colored solid at room temperature. That's also right because the intensity of color of the halogens increases on the group. Like fluorine is a pale yellow gas. Chlorine is a pale green gas. Bromine is an orange liquid. Okay, and even the physical states become like it's gas to liquid solid. And I2 is a gray solid, although it's a purple gas in brown solution, but you know, naturally it's a gray solid. And then 82 will be a black solid. So that is also right. And so since all three of them are right, my answer is going to be A. Okay. 37. The diagram shows a molecule of a compound which is a flame retardant. Which statements about the structure are correct? Each brominated carbon atom is chiral. See, this has. See, I don't see any symmetry in this molecule, do I? Symmetry. I don't really see symmetry. I mean, it's a very complex molecule. It doesn't seem to have any symmetry because there's one Br here, but no matching one here. Those are here, but then there's no access to symmetry basically. So this is chiral, this is chiral, this is chiral. Yeah, all of them are chiral really. So each brominated carbon atom is chiral. That's right. Now, next one, C12H20Br6. That's the molecular formula. Let's check. So I have one H atom here, two here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. I got 18. So my count for hydrogen is not right. Let me just count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Should be right. 18. Okay, so I got 18. Oh no, no. I got 18. And 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 carbon atoms definitely, and then bromine is 1, 2, 3, 4, 5, 6. That's 6. So I got C12H18 Br6, which is not what the statement says. So that means this might be wrong. CCC bond angles are all 120 degrees. 120 would mean that the carbon has a double bond somewhere, but there's no double bond. So it's because you're taking carbon, so there's no double bonds, which means that that's wrong. So it's all of them are 109.5 degrees because each carbon forms 4 single bonds, sigma bonds, right? for single sigma bonds. Anyways, the point is that the answer is just D. Okay. So yeah. Next, okay, so which changes in bonding occur during the reaction of propanol and hydrogen cyanide? I have propanol and hydrogen cyanide. They're asking about bonds, so I think it's better if I draw them out. So let me draw out even propanol. CH3CH It looks prettier if I make it like this COH, right? Okay. Plus HCN, obviously. Now that will it's a nucleophilic addition reaction, right? Which means only one particle is formed. So CH H CH O H C N. That's it. So that's the product that's formed. It's nucleophilic addition, so only one product is formed. Now a carbon hydrogen bond is broken. Is it? This bond is broken, right? See that? So it's broken. So that's one carbon hydrogen bond. I can say that's broken. That's definitely right. An oxygen hydrogen bond is formed. This bond is formed, which was not there before. So I would say this is also right. A carbon carbon bond is formed. Although this one is broken. Anyways, a carbon carbon bond is formed. Let me see. Yeah, it is formed definitely. See this bond. This is a carbon carbon bond that was not there before. See, right? So I would say that all three options are right, and the answer is A. Okay. Which pairs of reagents will react together in a redox reaction? Redox reaction. Let's see which ones give me a redox reaction. CH3CHO plus Felling's reagent. Okay. So Felling's reagent is actually CuSO4 aqueous, which is a blue, or let's say clear blue solution, perhaps clear blue solution or a pale blue solution, you could say as well. Anyways, it's a blue solution, okay, light blue. So CuSO4, when it reacts with an aldehyde, it becomes CO2O. Okay, so over here CuSO4, the Cu has an oxidation state of +2. Okay, Cu2 plus and SO4 2 minus. In CO2O is copper 1 oxide, which means it has a +1 oxidation state. All right, so it's going from +2 to +1. And if you check out CH3CHO as well. Well, let me just see CH3CHO, and it's becoming. So this is actually what do you call it? +2 to +1, so it's reduction, right? So this is reduction, and CH3CHO in the presence of Fehling's reagent, like it's an aldehyde. In the presence of Fehling's reagent, it is oxidized to CH3 CO2H, which is carboxylic acid, right? Ethanoic acid. So reduction is taking place and oxidation is taking place. Oxidation is taking place. So then, since both are taking place, reduction and oxidation, so it's a redox reaction, obviously. So one is right. Okay, hope that makes sense. Now I'll go to B. Sorry, number two. Oxygen. Question. Option number two. So C2H4 plus Br2. Um, C2H4 plus Br2 seems to be an addition reaction, electrophilic addition reaction, right? So C2H4 plus Br2 gives you C2H4 Br2. Now, over here, hydrogen has a fixed oxidation state of +1, so +1 times 4. Carbon, I'm going to find the oxidation state of +2x is equals to 0 because there are two carbon atoms of 2. Then 2x is equals to -4, so x is equals to -2. So over here, basically my carbon has an oxidation state of -2. Okay, Br2, that is oxidation state of 0 because it's pure elemental state. And here, again, because this has a fixed oxidation state of +1, so totally the total of +1 times 4 is basically +4. So I need to divide +4 between two carbon atoms and Br. So I could make this as, well, this could be -2, and this could be -1. So then -1 times 2, because there are two carbon atoms, plus 4 in total. And then -2 for the Br equals to 0, right? -2 plus 4 minus 2 is 0, right? So that's just, I was just checking if it's right. It does seem right. So then, Let me check if this is a redox reaction. Carbon is going from -2 to -1. -2 to -1 means its oxidation state is increasing, so it's becoming oxidized. 0 to -2, on the other hand, for bromine means that its oxidation state is decreasing, which means it's reduction. So reduction and oxidation are both taking place, which means again it's a redox reaction. Okay. And let us look at the last option, which is CH4 plus Cl2, which is probably a free radical substitution reaction. When I don't, yeah, why would it not be a free radical substitution reaction? Anyways, CH4 plus Cl2 is that would give me CH3Cl plus Cl. Okay, or in fact, let me make it HCl. Yeah. Over here, this has 0 oxidation state. This has -1 oxidation state because this is +1, so that's -1. And 0 to -1 is 0 to -1 would be like oxidation state is decreasing, right? So it's reduction. Okay. Over here, hydrogen has +1 fixed oxidation state, and there are 4 hydrogen atoms, so +1 times 4. To balance that, you need the carbon to have a -4 oxidation state, right? Because -4 plus 4 will be 0. So this is -4 here. Over here, chlorine. Um, well, let me assume chlorine to have -1, I suppose. Like if I assume it doesn't change. I mean, it does seem like a redox reaction, so I think I can make that assumption. And then this one will be +1 times 3. And so what will be the oxidation state of C equals to 0. So x plus 3 minus 1. So x is equal to x plus 2 then equals to 0. So x equals -2. Okay. So carbon here is -2. Wait, did I do that right? Hopefully. Yeah, so -4 and -2. So -4 to -2 is increase in oxidation state. So if it's an increase in oxidation state, it's oxidation, right? So if oxidation is taking place and reduction is taking place, both are taking place basically, then it's a redox reaction. So again, I got all three of them as redox reactions. So A seems to be the correct answer. Okay. Again, by the way, if I make mistakes, please correct me in the comments so that you know people can know what the right answer is. Anyways, which types of reaction undergone by CH2Br CH2? Let me draw it out. CH2. First, let me draw the scale formulas. CH2Br. So this might be it. And then CH2. So that should be it. Okay. But let me draw it out like this as well. Br CH2. Okay. Yeah. So does it undergo hydrolysis? Hydrolysis? I don't know if it's hydrolysis or hydrolysis. But anyways, yes, it does because this halo, it's a haloalkane from this part, right? So the haloalkane can undergo a hydrolysis reaction with NaOH or KOH in aqueous solution. Okay, so definitely yes, it can undergo hydrolysis. And then free radical substitution, yes, because as I mentioned, it's a halogen alkane, right? So the alkane thing means that yes, it can undergo free radical substitution. That's this could be replaced by chlorine, for example, or whatever, right? Now nucleophilic addition, can it undergo nucleophilic addition? Nucleophilic addition is characteristic of ketones or aldehydes, right? So basically, carbonyl compounds, ketones, aldehydes. I don't see. Oh no, can sorry about that. Okay, so I don't see. See, I see a halogenoalkane group, but and I see um an alkene group, but I do not see a carbonyl group, right? I don't see ketone or aldehyde here, so that means that it does not undergo nucleophilic addition, and therefore, since only 1 and 2 are correct, that means the answer must be B. Okay, so yeah, the answer is B. Now the whole paper is done. It's been a long time since I did a paper, but I enjoyed it very much. So hope you guys benefited from the video, and if you have any specific past papers you want me to do, you can tell me in the comments. Okay, thank you very much for watching.